following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
One of the cutest little data structures that was ever invented, called a heap. And we're going to use the heap as an example implementation of a priority queue. And we'll also use heaps to build a sorting algorithm called heap sort that is very, very different from either insertion sort or merge sort. And it has some nice properties that neither insertion sort nor merge sort have. But what I want to do is get started with motivating the heap data structure, regardless of whether you're interested in sorting or not. So the notion of a priority queue, I think, makes intuitive sense to all of you. It's essentially a structure that implements a set S of elements and each of these elements is associated with a key. And as you can imagine, a priority queue is something where you queue up for something, you want to buy something, you want to sell something, you have certain priorities assigned to you, and you want to pick the maximum priority or the min priority. You want to be able to delete it from the queue. You want to be able to insert things into this queue. You want to be able to change priorities in the queue. So all of these operations are interesting operations that should run fast, and for some definition of fast. Obviously, we are interested in the asymptotic complexity definition of fast. In that case, we'll be saying, does this operation run in order n time, order log n time, etc. So in general, I think for the next few lectures, you're going to see a specification of a data structure in terms of the operations that the data structure should perform. And those of you who have taken 6005, you'll see that it's basically an abstract data type that's associated with this, these operations. So it's the spec for the abstract data type. In 6005, you didn't really spend a lot of time on asymptotic complexity or the efficiency of operations on the abstract data type. Here in 006, we'll specify this ADT and specify the set of operations or methods in the ADT, and we'll talk about whether these are order n complexity or order n log n complexity, and compare and contrast different ADTs. So today's ADT is a heap. And so what is the set of operations that we'd like to perform on a priority queue? So we can use that to motivate the development of a heap. And those are insert SX. So you have a set of elements S, and you want to be able to insert element X into set S. You want to be able to do max of S, which is return the element of S with the largest key. And different from max of X, S rather, is extract max of S, which not only returns the element with the largest key, but also removes it from S. So this is, you have a queue, and the person in the queue was serviced, or the element in the queue was serviced and then removed from the queue. And finally, you can imagine changing the priority of a particular element X in the set S, and this priority, there's an associated key as we have up there with each element, and that key is, call it K, and increase key S, X k would increase the value of x's key to the new value k. Right? And k could correspond to, it's just called increase. Most of the time, you're increasing the value in maybe a particular application. You could have certainly a decrease key, and you'd have to know what the previous value was. And it's just a matter of exactly what operation you want to perform. You could call it update or increment, whatever you like. I'm going to spend most of the time here talking about how you maintain a rep invariant of this data structure called the heap that allows you to do these operations in an efficient way. And we'll talk about what the efficiency is, and we'll try and analyze the efficiency of these algorithms that we put up. All right? So let's talk about a heap. A heap is an implementation of a priority queue. It's amazingly an array structure, except that you're visualizing this array as a nearly complete binary tree. And so what does that mean exactly? Well, the best way to understand that is by looking at an example. We've got 10 here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here's my array of 10 elements, and the elements are 16, 14, 10, 8, 7. So some set of elements, they're in random order, clearly not sorted. And I'm looking at the indices, and I'm looking at the elements, and I'm going to visualize this as a nearly complete binary tree. It's not a full binary tree because I only have 10 elements in it, and it would have to have 15 elements to be a complete binary tree. And we want to be able to do the general case of an arbitrary size array, and so that's why we have a nearly complete here. So what does it mean to visualize this as a tree? Well, index 1 is the root of the tree, and that's an item with the value 16. And what I have are indices 2 and 3 are the children, and 4, 5, 6, and 7 are the children of 2 and 3, and 8, 9, and 10 are the children of 4 and 5 in this case. And so that's the picture you want to keep in your head for the rest of this lecture. Anytime you see an array, you say we're looking at the heap representation of the array. The picture on the right tells you what the heap looks like. And so I'm not going to fill in all of these. You can, but I'll do a couple. So you have 10 here, and 8, 7, etc. So that's a heap structure. So what's nice about this heap structure is that you have a tree representation of an array, and that lets you do a bunch of interesting things. What do you get out of this visualization? Well, the root of the tree is the first element, corresponding to I equals 1. The parent of I is I over 2. The left child of I is 2i, and the right child of I is 2i plus 1. All right. So that's essentially what this mapping corresponds to. Now, on top of that, this is just what a heap corresponds to. We're going to have particular types of heaps that we'll call max heaps and min heaps. And as you can imagine, max heaps and min heaps have additional properties on top of the basic heap structure. So this is essentially a definition of a heap. Now I'm going to define what the max heap property is. And the max heap property says that the key of a node is greater than or equal to the keys of its children. Okay, that's it. It's obviously recursive in the sense that you have to have this true for every node in the tree. And when you get down to the leaves of the tree, they're not children corresponding to the leaves, so that's a trivial property. But at higher levels, you're going to have children, and you have to check that. So if you look at this example here, maybe I should fill this whole thing out. So I have 8 and 7 here, and 6 would be 9, and I have 3 over here, and then 2, 4, 1, right? So we can look at this and check whether it has the max heap property or not. Does it have the max heap property, this heap? Yeah, all you have to do is look at these nodes, 1, 2, 3 indices, index 4, 5, 6, and well, you don't have to look at 6 and 7 because they don't have any children. But you could stop with 5 here, and you look at the children, and there you go. The parent is greater than or equal to either of its children or its only child in the case of node 5, and so you have the max heap property. Right? It's a fairly straightforward property, and you can imagine defining the min heap property in an equivalent way. All right? Just replace the greater than or equal to with less than or equal to. So right off the bat, what operation is going to be trivially performed on a max heap? This is kind of a trivial question, but yep. Just finding the biggest element. Exactly right. The max operation. Now, what about extract max? Is that trivially performed on a max heap? No, because so what do I mean by that? When you say a max is trivially performed, what it means is that you can return the max, you can find the maximum element or a maximum element, and you obviously don't modify the heap. The heap stays the same, so it stays a max heap. In general, when we talk about data structures, and this goes back to rep invariance, which I mentioned already, you typically want to maintain this rep invariant, and so the rep invariant of our data structure, in this case, is a max heap property. Okay, so we want to maintain the max heap property as we modify the heap. So if you go from one heap to another, you start with the max heap, you want to end with the max heap. Okay, and it makes perfect sense because one of the simplest things that you want to do in a priority queue is you want to be able to create a priority queue, and you want to be able to run extract max on the priority queue over and over, right? And what that means is that you take the max element, you delete it, take the next max element, delete it, and so on and so forth, and there you go. All right? And it's a bit of a preview here, but you can imagine that if you did that, you would get a sorted list of elements in decreasing order, right? So you see the connection to sorting, because you could imagine that once we have this heap structure and we can maintain the max heap property, that we could continually run extract max on it, and if we could build extract max in an efficient way, we might have a fantastic sorting algorithm. All right? So the big question that really remains is how do we maintain the max heap property as we modify the heap, okay? And how would you go? The other question, which I haven't answered, is there's this array that turns out it was a max heap, okay? But it's quite possible that I have a trivial example of an array in fact, let me make this 1. That is not a max heap. It's not a max heap, it's not a min heap. It's neither, right? It's just a heap, okay? So if I just transform or visualize, I should say, this array as a heap, I don't have a max heap, I don't have a min heap. So if I were interested in sorting, and I am, there's another thing that's sort of missing here that we have to work on, which is how are we going to build a max heap out of an initially unsorted array, right? Which may or may not turn into a max heap. This trivially happened to be exactly the right thing because I picked it and it turned into a max heap just by visualizing it. But it's quite possible that you have arrays that are input to your sorting algorithm that look like that, right? Yep. Okay. So let's dive into heap operations. I'm going to have to spend some time describing to you a bunch of different methods that you would call on a heap. And all of these methods are going to have to maintain our representation invariant or the max heap property. So what are the heap operations that we have to implement and analyze the complexity for? Well, we're going to have build max heap, which produces a max heap from an arbitrary or unordered array. So somehow I got to turn this into, for example, 4, 2, 1, okay? Which is in effect sorting this array, right? Or changing the order. Maybe not fully sorting it, but changing the order. So that's what I'll have to do. And build max heap is going to have to do that. In order to do build max heap, the first procedure that I'm going to describe to you is called max heapify, right? Heapify, right? Sounds a little strange, but I guess you can ify pretty much anything. So you correct a single violation of the heap property in a subtree's root, okay? And I'll explain what I mean by that in just a minute. So max heapify is the fundamental operation that we have to understand here, and we're going to use it over and over. What it does is take something that is not a heap, not a max heap. When I say not a heap from now on, pretend that I'm saying not a max heap. We're only going to be talking about max heaps for the rest of this lecture, okay? What max heapify does is take something that is not quite a max heap. It can't take anything arbitrary. It's going to take something where there's a single violation of the max heap property at some subtree of this heap that is given to you, and there's a single violation of that. And it's going to fix that, okay? And we need to be able to do this recursively at different levels to go build a max heap from an unordered array. And then once you have that, you can do all sorts of things like insert and extract max and heap sort and so on and so forth. So let's take a look at max heapify using an example. I'm not going to write pseudocode for max heapify, I'll run through an example, and the pseudocode is in the notes. The big assumption, and you can think of this as a precondition for running max heapify, is that the trees rooted at left eye and right eye are max heaps. Right? So max heapify is going to look like A comma I. A is simply the array, and I is the index. Okay? And max heapify is willing to, you're allowed to crash and not do anything useful if this precondition is violated in max heapify. But if the precondition is true, then what you have to do is you have to return a max heap correcting this violation. All right? That's the contract. So let's take a look at an example. I think what I want to do is start over here. I want you to see all of the steps here. So we'll take a simple example and we'll run through max heapify. And let's take a look at 16.4. And I'm just going to draw the indices for this first example, and then I won't bother. So there you go. Is this a max heap? No, because right here I got a problem. 4 is less than 14, therefore I have a violation, right? And so if you look at the call max heapify 8, 2, this is an index 2, and all you have to do is to look at this subtree, and what you need to be satisfied in order to run max heapify is that the subtrees of node index 2, which is this 4 node, are max heaps. And if you go look below, you see that this is a max heap and that's a max heap. Okay? Most of the time, by the way, you'll be sort of working bottom up. And that's why this is going to make sense, right? This will all work out because leaves are, by definition, max heaps, because you don't have to check anything, right? When you put two leaves together and you want to create a tree like that or a heap like that, then you run max heapify. And then when you have a couple of different max heaps and you want to put them together to make it a bigger max heap, you'd have to run max heapify, right? So that's the way it's going to work. So you want to do a max heapify A, 2, and one of the things that's going to be important, not in this example, but when we get to sorting, is that we want to know what the size of the heap is, and in this case, the heap size is 10. Right? So what does max heapify do? Well, all max heapify does is exchanges elements. And so if you looked at the code for max heapify and you walk through it, this is what it would do. You're going to look at 4 and 14, and it's going to say, OK, I'm going to look at both my children, and I'm going to go ahead and exchange with the bigger child. So I'm going to exchange A2 with A4. And what that would do is take this, make this 4, and make this 14. And that would be step 1. And then when you get to this point recursively, you'd realize that the max heap property at this level is violated. And so you would go ahead and call max heapify a comma 4. And when that happens, or that call happens, you're going to look at the two children corresponding to this little subtree there, and you're going to do the exchange. You're going to have 8 here and 4 here. So you would exchange A4 with A8. And now you're done, so there are no more calls. All right? So fairly straightforward. It's actually not any more complicated than this. There may be many steps. What might happen is that you'd have to go all the way down to the leaves. And in this case, you went a couple of steps, and then you got to stop. But obviously, you could have a large heap, and it could take a bunch of time. So what is the complexity of max heapify? Anybody? Yeah, back there.
Well, it seems like you could potentially, if the tree is totally upside down, you could potentially have to switch every node to make it order n.
Every node to make it order n. Anybody agree? You have a different answer?
Log n.
Why? Why is it log n?
Because I think, well, in the worst case scenario, all of your, like the worst case scenario, you'll have two n over 3 nodes on the left-hand side and n over 3 on the right-hand side. Right? It will be like skewed.
Okay.
Right? And so your recursive call will be for t of n over 3 plus a constant.
Yeah.
And so you just keep calling that over and over again. So it'll be like t of n over 3. Well, t of n is less than or equal to t of n over 2n over 3 plus.
So you're arguing that the solution to the recurrence gives you a logarithmic complexity. All right, not quite. There's an easier way of arguing this. Yeah, back there. That's right. That's right. So what is the complexity?
Log n.
Log n. Great. Good. Excellent. Definitely worth the cushion. Whoa. Missed you by that much. All right. It's pretty soft, by the way. Right. Okay. So if I hit somebody, they get a cushion. Okay. All right. So that's exactly right. Thanks for that description. So first off, there's two important aspects to this argument. The first thing is that we're visualizing this as a nearly complete binary tree. Okay. It is not an unbalanced tree. All right. We'll talk about unbalanced trees and balanced trees in the next couple of lectures. But the visualization of a heap is a nearly complete binary tree. And in fact, if you had 15 elements, it'd be a perfect binary tree. Okay? So the good news is that the height of this visualization tree is bounded by log n. Okay? That's the good news. All right? And you want to exploit that good news by creating algorithms that go level by level. Right? If you can do that, you're going to have logarithmic complexity algorithms. All right? And so that was one aspect of it. The other aspect of it is the key assumption that we're making with respect to build max heap, that there was a single violation. All right? It is true that the answer that was given, that was order n, would be a problem. I could set it up so that's actually the right answer if I did not have this assumption. Where do I have that here? Assume that the trees rooted at left eye and right eye are max heaps. Okay? So maybe that's what you were thinking. But this is a key assumption. This is, going back, and I like making connections between classes. This is a precondition that makes the algorithm more efficient, makes the implementation easier. And this precondition essentially says that you have to just go down and do a number of steps. That's the number of levels in the tree, which is logarithmic. All right? So that's the story here with max heapify. It's order log n in terms of complexity. That's the number of steps that you have. And it's a basic building block for all of the other algorithms that we look at for the rest of this lecture and in section tomorrow. Let's talk about how you would take max heapify and use it to do build max heap. So the first step, now let's say that we want to go and get a nice sorting algorithm. We don't like insertion sort, we don't like merge sort. We'd like to get a heap-based sorting algorithm. One of the things that we need to do, as I said, is to take an unordered array and turn it into a max heap, which is a non-trivial thing to do. And once we do that, we can do this extract max deal to sort the array. So the first step is we want to convert an array A1 through n into a max heap. And the key word here is max heap, because every array can be visualized as a heap. And I'm going to write the pseudocode for build max heap, because it's 2 lines of code. And that's about the limit of the size of program I can really understand, or explain, I should say. And this is what it looks like. All right, that's it. Build max heap says go from I equals n by 2 down to 1, okay? Max heapify A of I. All right? So someone explained to me and why I can start with n over 2 and why I'm going down to 1. Yep, I saw you first. Leaves are good, good. So leaves are good. I'll let you go on for a second, in a second. Leaves are good because if you look at elements A of n over 2 plus 1 through n are all leaves. Okay? That's a good observation. All right? And this is true for any array. All right? Doesn't matter what n is. Doesn't have to be a power of 2 or 2 raised to n minus 1 or anything like that. So, and leaves are good because they automatically satisfy the max heap property. Continue.
Okay, so after that, we start from next level up.
Yeah.
And we keep dividing.
That's right.
So as we go work our way up the tree,
Yep.
we get to the root. So when we reach an element, we know that everything below it has already been defined.
That's exactly right. So beautiful. Won't hit anybody here. So that's it. The reason this works is because you're calling max heapify multiple times, but every time you call it, you satisfy the precondition. Okay? And the leaves are automatically max heaps. When you start with n over 2, you're going to see 2 leaves as your children for the n over 2 node, right? I mean, just pick an example here. N over 2 is A of 5, right? And so you're out here, right? And in this case, depending on the value of n, you may have either 2 children or just 1 child, and you have 1 child. But regardless of that, that's going to be a max heap because it's a leaf, right? And so you'll have 2 leaves, and you need to put them together. And that's a fairly straightforward process of attaching the leaves together. You might have to do a swap based on what the element is. One operation, and you get a small little tree that's a max heap. And then you do a bunch of other things that all work on leaves, because n over 2 minus 1 is probably also going to have leaves as its children, given the large value of n. And there'll be a bunch of things where you work on these level 1 nodes, if you will, that all have leaves as children. And then you work on the level 2 nodes, and so on and so forth. And as I said before, you're working your way up, and you're only working with max heaps as your left child and your right child. All right? That makes sense? All right. So if you do that, and this is a fairly straightforward question, and if you do a straightforward analysis of this, what is the complexity of build max heap? Yep. Right, so that's order. order n log n. Okay. Now, this is through a simple analysis. Now, I'm going to give you a chance to tell me if you can do better than that or not in terms of analysis. Okay. So here's it's a subtle question. All right. It's a subtle question that I'm asking. I'm saying this is the algorithm. All right. I don't want you to change the algorithm, but I want you to change your analysis. Right. The analysis that you just did was you said I got theta n steps here because it's n by 2 steps. Looks like each of the steps is taking log n time. So that's n log n. And I was careful. I put big O here, okay? Because that's an upper bound. So that's a valid answer, right? Can you do better? Can you do a better analysis? And I'll let you go first. Can you do a better analysis that somehow gives me a better complexity?
I think you can bring it to n complexity.
Okay, well, how?
So each node takes a maximum of 2 comparisons.
Yep.
To determine the correct notation.
All right.
So for some n, there will be a constant number of comparisons to max heapify that all these things below it. So that will be
Yeah, it's hard to explain. You're on the right track. You're absolutely on the right track. So it turns out that, and I'll do this, it's going to take a few minutes here because I have to write some things out. We got to sum up a bunch of an arithmetic series and so on. So it's a bit unfair to have to speak out the answer. But the correct answer, in fact, is that this is order n complexity. Okay, this algorithm that I put up here, if you do a careful analysis of it, you can get order n out of it. Okay, and we'll do this careful analysis. And I'll tell you why it's order n in terms of sort of a hand-wavy argument. Okay, the hand-wavy argument is that you're doing basically obviously no work for the leaves, but you're not even counting that because you're starting with n over 2. But when you look at the n over 2 node, it's essentially one operation or two operations in whichever way you count to build max heap, right? And so for that first level of nodes, it's exactly one operation, that the first level that are above the leaves. For the next level, you may be doing two operations. And so there's this increase in operations as you get higher and higher up, but there's fewer and fewer nodes as you get higher and higher up, right? Because there's only one node that is the highest level node, the root node. That node has logarithmic number of operations, but it's only one node, right? And then the ones down at the bottom have a constant number of operations, okay? So I'll put all of this down, and hopefully you'll be convinced by the time we've done some math here, or arithmetic here. But you can quantify what I just said fairly easily as long as you're careful about the accounting that we have to do. So this is really truly accounting. Analysis has a lot to do with accounting, and we're just being more careful with the accounting, as opposed to this straightforward argument that wasn't particularly careful with the accounting. So let's take a look at exactly this algorithm, and I want to make an observation, which is what I just did, but I'd like to write it out, where we say max heapify takes constant time for nodes that are one level above the leaves, and in general order L time for nodes that are L levels above. The leaves. Okay? That's observation number 1. Observation number 2 is that we have n over 4 nodes with give or take 1, depending on the value of n. I don't want to get hung up on floors and ceilings. And in any case, we're eventually going to get an asymptotic result, so we don't have to worry about that. But we have n over 4 nodes with level 1, n over 8 with level 2, and 1 node at log with log n at sort of the log n level, okay, which is the root node. Okay, so there's this decrease in terms of nodes as the work that you're doing increases. All right, and that's the careful accounting that we have to do. And so all I have to do now to prove to you that this is actually an order n algorithm is to write a little summation that sums up all of the work across these different levels. And so the total amount of work in the for loop can be summed as n divided by 4 times 1 times c. So there's some, I have one level here, and I'm going to do some constant amount of work for that one level. All right, so I'm just going to put c out there because eventually I can take away the c, right? That's the beauty of asymptotics, right? So we don't need to argue about how much work is done at that one level, how many swaps, et cetera, but the fact is that these n over 4 nodes are one level above the leaf, right? That's what's key. And then I have n over 8 times 2c plus n over 16 times 3c plus blah, blah, 1 times log of nc, right? I'm essentially written in an arithmetic expression exactly what I have observed on the board above. All right? Stop me if you have questions. Now, I'm going to set, just to try and make this a little easier to look at and easier to reason about, I'm going to set n over 4 to 2 raised to k, okay? And I'm going to simplify and just pulling out certain things, and this thing is going to translate to c times 2 raised to k times 1 divided by 2 raised to 0, 2 divided by 2 raised to 1, 3 divided by 2 raised to 2, etc., k plus 1 divided by 2 raised to k. Okay? If that was confusing, raise your hand, but it's essentially identical given the substitution and sort of just applying the distributive law. All right? And the reason I did this is because I wanted you to see the arithmetic expression that's in here. Now, we do know that 2 raised to k is n over 4, of course. But if you look at this expression that's inside here, what is this expression? Anyone? Can you bound this expression? Someone? What the cushion? Remember your arithmetic series from wherever it was? Geometry? Yeah, you know better than I. I guess you took those courses, more recently. So what happens with that? I mean, those of you who have calculators, I mean, you could plug that in and, answer that. Yeah? No one? Yeah, go ahead. That's exactly what I was looking for, right? Essentially, well, it's not quite 2 because you have a 1 here and you have a 1 here, but you're exactly right. I mean, 2 is good. Is asymptotics. I mean, come on. I'm not going to complain about 2 versus 3, right? So the point is, this is bounded by a constant, okay? It's bounded by a constant, all right? This is a convergent series, and it's bounded by a constant, all right? And we can argue about what that constant is. It's less than 3, okay? And it doesn't matter even if k goes to infinity, right? I mean, you want k to go to infinity, but it doesn't matter if k is small or k is large. This is bounded by a constant, okay? And that's the key observation. So what do we have left? What do we have left? We have a constant there, okay? We have a c, which is a constant, and we have 2 raised to k, which is really n, okay? So there you go. There you have your theta n complexity. Okay, now I can say theta n, because I know it's theta n, right? But big O of n, theta n, that's what it is, right? So that was, I'd say, a subtle analysis, clearly a little more complicated than anything we've done so far. And let me see if there are questions. How many people got this? I did too, right? Okay, someone who didn't get it, ask a question. What didn't you get? What step would you like me to repeat here? Any particular step?
The step from N/4
to this thing here, right here? Okay, so you're not convinced that this expression got translated to this expression. All right, so let me try and convince you of that. All right, so let's take a look at each of the terms. Okay, n by 4 is 2 raised to k. I'm just looking at this term and this term. Okay, n by 4 is 2 raised to k. Right, c is c. All right, and I just wrote 1 as 1 divided by 2 raised to 0, which is 1. Okay, and the reason I want you to do this is because I want to show you an expression where, in some sense, this is the term that is the summation for your expression. If you just replace this with, you can write that out as I equals 0 through k, I plus 1 divided by 2 raised to I. All right, that is the symbolic form of this expression which came from here. All right, and then the argument was made that this is a convergence series and is bounded by a constant. All right, that makes sense? Good. So that's pretty neat, right? I mean, you had the same algorithm, and voila, it suddenly got more efficient, right? Doesn't always happen. But that tells you that you have to have some care in doing your analysis, because what really happened here was you did a rudimentary analysis. You said this was order log n, big O log n, and you said this was theta n, and you ended up with this. But in reality, it's actually a faster algorithm. All right? So that's the good news. Build max heap can be done in order n time. Now, in the time that I have left, it turns out we're essentially all the way to heap sort, because all we have to do is once we have build max heap, I'll just write out the code for heap sort, and you can take a look at examples in the notes, the pseudocode, I should say, for heap sort. And it looks like this. The first step that you do is you build max heap from the unordered array. Okay. Then you find the maximum element, A1. All of this I've said multiple times. Now the key step is you could do extract max, but one nice way of handling this is to swap the elements an with a1. Okay, and let me write this out and I'll explain exactly what that means. Now the maximum element is at the end of the array. Okay, when you do the swap. That's the one step that I'll have to spend another minute on. Now we discard node n from the heap simply by decrementing heap size. So the heap becomes n minus 1 in size from n in the first iteration. Now the new root, which after the swap may violate max heap, we'll call it the MHP, the max heap property, but the children are max heaps, because that's the one node that can possibly violate it. So what that means is we can run max heapify, to fix this. And that's it. Once you do that, you go back to that step. So what's happened here exactly? Well, this part you know we spent a bunch of time on. You know that the top element is the maximum element. So you grab that, and you know that that's the maximum element. You don't want to just, one way of doing it is to use extract max. But rather than doing extract max, which I haven't explained to you, you can imagine that you go off and you swap the top element with the bottom element, and then you discard it. So here's a trivial example where, let's say I had 4, 2, and 1, which is the max heap. What would happen is you'd say, I'm going to take 4, and I'm going to swap it with 1. And so you have 1, 2, and 4. Now, 4 used to be A1, and that's the maximum element. And I'm just going to delete it from the heap, which means I'm going to end up with a heap that looks like a heap, not a max heap, that looks like this. And I write down 4 here. 4 is the first element in my sorted array. Now I look at 1 and 2, and 1 and 2, this is obviously not a max heap, but I can run max. I know that the child is a max heap, so I can run max heapify on this. And what this turns into is 2 and 1. Okay? And at this point, I know that the max is the root, because I've run max heapify, and I take 2 out. And at this point, after this, it becomes trivial. But that's the general algorithm. So this whole thing takes order n log n time, because even though build max heap is order n, the max element is constant time. Swapping the elements is constant time. But running max heapify is order log n time. And you have n steps. So you have an order n log n algorithm. But the first step was order n, which is what we spent a bunch of time on. So I'll show you, there are examples in the notes, and you'll get covered again in section. I'll stick around for questions. See you next time.